So good morning, how are you? And suddenly it's getting cold. It's very nice. I'm going to assign a few homework problems, and you got 2-page handout. If you look at read the cover of the book, Hikyu has 2 sets. You can check out, make a copy for the page for the examples. It has a really complete solution there. And I want you to go through the process of solution. Just go through it. So if I say to go through it, please really go through it. You can really resolve the problem set. So that will be whole basis of like midterm exams and all that. Because as I announced it, I am going to give you some other kind of the example problem. Some are close to what the example shows. So don't just read it. Just go line by line, then understood what's going on. Then if you still have a little problem, see me. Then I can help you out. But it's very straightforward. 3 problems. And the other problem set is the first page of handout, the page 1G-1. I'm going to cover, of course, today the skewness and kurtosis, but you saw it already last Friday for you through the presentation. But if you look at second bullet item, measure of correlation, I'm going to talk about Aline, you have a handout? Thank you. 2-page. If you don't get it, you have to say something, otherwise you're not going to get it. Okay, measure of correlation is the lecture, part of the lecture item I'm going to do this morning. But this is like a summary sheet, okay? And 1, item 2, item 3, item 4, item 5, is I'm gonna go through all the derivations and meaning of it. What do you do for such a correlation coefficient to things like that? But item number 6 through 11, I give you the relation, but I want you to derive the relations. Okay, and item number 6, what's a VAR? It's a variance, right? It's VAR is the variance. You will see today too. Well, we covered that already. Variance. What would be COV? You haven't learned that yet, but What can you say, Isu? Covariance. You will see that. But this is a little bit ahead, okay? C of V is covariance, and you will taste not only definitions and some use of it, you can think of use of it is covariance, and the items, homework number 2 is really item number 6 through 11 that drive the relations. Okay. So over here, what you need, we'll cover, as I said today. So I said variance of x. This is a variance. And COV, we use COV, which should imply something else. What was it? Coefficient of the variation. You remember that? Coefficient of variation. What's the definition of coefficient of variation? Which is sigma over the mean. What's a sigma? Aline, what's a sigma? Standard deviation over the mean. It's a measure of the variability. It's normalized standard deviations. It's a measure of dispersion of population of the data. This is a covariance. So covariance, I'm going to say x1, x2. So capital letter implies the random variable. And there's 6 through 11, so it's about 6 problems that you can nicely derive. And due is always week after. So Monday next Monday. Okay. Before I get to the properties of probability functions like skewness and kurtosis, I'm going to introduce the joint probability density function and the probability distribution function. And before, sometimes after lunch, Higyu, Higyu is a teaching assistant, right? So Higyu is going to help me and help you. So I'm gonna send him my handout, so he can just distribute the handout to all of you. But that's not really identical to the all the lectures. It's combined. Some are in the book, then I don't have to really repeat to sending the same item. But it's kind of a condensed some lecture notes, you can say. So by the way, I was going to go up the Sowell Walker Hill Hotel for a conference. They have a still, I think structure engineering mechanics conference up there, which is sponsored by really KAIST, by the Professor Chang Gun Choi in civil engineering. I also involved a little bit on the work of the Journal of Ocean Systems Engineering, but most 700 people are coming there. And ocean engineering, systems engineering is about maybe 20 papers, even less. It's just the beginning. So all others structural engineering, mechanics. So I got some other some family affairs to do tonight, so I decided not to go. So I'll be here all the time. So if you have to see me, just stop by to my office, okay? Okay, so joint probability, joint. Some of you, I understand, I learned already, but look at some other side of the meaning, some applications in your area, vice versa. Joint probability density function, you are dealing with the two random variable here. It can be multi-number of the variable. So of course, first I can say FYR, very distinctive. This is a probability distribution function. Distribution functions confused. Don't confuse. The better way is better way to say is cumulative distribution function to avoid any confusion. PDF is probability density function is what we are using it. And fxy, joint probability distribution function or cumulative distribution function is just a joint, two random variable xy. This is a probability such that x is less than equal to x and the y is less than and equal to y. So two random variable x, y, capital x and y are random variable, and x and y are the specific variable. So it's really specified the variable. So you can say that. So x, so here, for example, if I draw the graph, if it is a function of one random variable, then probability distribution function or density function is going to be just a 2D if it's as you saw, is simply like if it's x, then this is fx. If it's one random variable, for the two random variable, it's going to be the volume curve. So to get the distribution function, you simply calculate the area under the curve. If it's a joint probability function, then what do? You have to the computer calculate the volume under the fxy. So by doing that, you have to draw the 2D. For example, this is x-axis, this is y-axis, and this is the z-axis. This is going to be fx, y, x and y. So I can draw just a cut along the x-axis to y. So here is to look at the contour, you can write contour line there. Okay. So this is so if you compute the area as you have done, not area, volume, like you have done in one random variable situation, you can compute the cumulative, distribution function. So here, x has to be less than equal to infinity. Of course, y is less than or equal to infinity. That's very straightforward. However, if I say fxy minus infinity to y is equal to, can you visualize this 3D graph, which is small fxy? X is approaching to negative infinity. Visualize it. And y is any value. Okay? What would be the result? You have to keep visualize one variable out of two going negative infinity. Then this end, for example, if it really goes like all the way here, it's going to approach to the x-axis. Think about as it approach. Y can be any. If it's along just a cut right at the x-axis, what the value would be? As it, you assume the y is 0. This plane here, then this is going to go approach to louder 0. You can cut any place, any location at y is equal to 100. Then you look at this direction as x approaches to negative infinity, then the value goes to the 0. You see that? Visualize. This is 0. What happens if you look at fxy? This is x approach to y is approaching to negative infinity. It works as the same way. It's equal to, it's a property. For example, this set is like a property. Then what about fxy? infinity to infinity. XY directions are infinite to infinite. What would be it? Which means it covers the whole volume, right? Well, it's just the volume, total volume under the surface, which is, when I say surface, which is the really small fxy surface, then the total volume would be 1. Total volume. Probability it happened is 1. So for the single random variable of x, all total area under is when x goes to infinity is equal to 1. So same thing. This is equal to 1. So to compute the structure reliability, which would be the probability of the survivor, or 1 minus probability of the failure, is we'll start from something like 2 random variable soon, but in fact it's a multi-number of random variable. For the integration, it's so difficult. So that's the major issue for structure the reliability calculation. So this book cast to solve the volume using optimization technique. First, using as approximation linear programming technique, and expand into the nonlinear programming technique. That's what the base of the optimization. Then if you try to follow, it's almost impossible. Well, not impossible, without background of the linear and nonlinear programming technique. So there is a direct approach to really taste the fact, what's in the structural reliability. That's what I'm going to really concentrate on, that first order and second order, the reliability function calculation approach. And of course, Monte Carlo method is what I'm going to do it really with you. So then you can really program the first order. Second order is too messy, so we'll stay in the first order to solve real problems and things like that. Okay, so now this is a probability distribution function or cumulative distribution function. What about the probability, joint probability density function? Always start from the definitions. So definition here is a limit delta x goes approach to 0, delta y approach to 0. So probability such that x, capital X, x plus delta x and the y, capital Y, if you look at carefully, it's a tangential plane, which really tangential plane at any point, at any given point on the surface. So that's what the really capital fxy for the density function. So okay, definitions and fxy is fxy can be the negative, always the density function, or cumulative distribution functions are greater than 0. So this is always greater than 0. And density function minus infinity to infinity fxy, xy, integration of whole fxy, which means is really the volume dx dy, is equal to it's a 1. That's a total volume. Double integration is equal to 1. So mathematically, then fxy, xy is equal to minus infinity to x specific point y specific, and fxy, I can say integration parameter is d alpha, d beta. This is still definition for joint probability density function. So now from here you can derive fxy you did for integration to get the capital fxy, and to get the density function, then you can differentiate, of course, you can differentiate xy once, then twice. Not much fun to keep introduce this, but without knowing the basic relation and definition, then you will be confused for next step. And if you integrate minus infinity to infinity about dy, okay, think about this 3D space, integrate along the y-axis dy, then all the y goes away. It's just condensed right out. Then this will be fx simply, x. And if you integrate out dx is equal to what? F y y. If you say x and y are statistically independent random variable, then what can you say? What can you say about independent variable? Still single each other. X is single, Y is single. They have no link between. Then it's a bachelor state. Then you should be able to split this into this. So this is connected by a marriage. Marriage, M-A-R-R-I-A-G, something like that. Yeah. And of course, for the cumulative function, it's going to be, condition over here is x and y are independent. So this is fx. That is about all. This is about basic definition of joint probability density functions and also probability distribution functions. That's about all. No more or no less. And I'm going to say a few words about its own personality characteristics. Okay. What do you call this notation? What do you call this notation? Expected value is a mean. So if it's a mean of x, one variable, what did you do? Integration of, for continuous function, of course, what did you do? Integration of x that's what you have done. But then if you look at x, y, now this function, of course, not independent each other usually when you deal with a joint probability function. Then how can you express? Of course, this is minus infinity. So it's a two random variable, expected value of two random variable. So you can say double integration, right? It's a double integration. So it's xy f you can find the mean. So now let's say x, y are independent. Independent random variable. To make it simpler, you usually, what the mathematician does is, as a special case, then after derive the joint probability function, then say, well, what happens if it's independent? If it's independent, calculation is really drastically easy to perform. Okay, so here, so we're gonna assume here, we're gonna assume the functional relation between x and y. Functional relation is, let's say, xy. Last Friday we learned to compute the probability of something like a y when the y is a function of x. So it's kind of that sort of the g. If you do that, E, by definition, E is E of the G. I don't have to say this, but it's a functional relations, okay? Relation between the x and y. So if you do this, then you can say this is two random variable, then gxy and fxy, xy, dx. Definition not looks, are very straightforward. But as I mentioned, computation can be very, very messy. Then here, I'm going to say let the gxy is equal to xy. So if I say this guy is xy, which are statistically independent each other, then you can say you can split x and y because it's independent. I can say this is equal to infinity y fy y. You can completely split. If x and y are independent, then you can bring this relation and split the term x and y completely. Then if you look at this, what do you call this? This is EX, right? What do you call this? This is equal to EY. So this is called EX, EY. Oops. EY, if we use a different notation, mu x times mu y is all the same. Here, I'm gonna finish all this probability stuff. Latest is really Monday, because from tomorrow I wanna really show you probability model. We have done the one model, normal distribution model. We're gonna do log normal distribution, which has a skewness in the system. So you will taste on that. Then we're gonna look at the y-ball extremal distribution. And as time permit, we're gonna look at one more. Otherwise, I'll just assign to you to spend the time in your office. Okay. So now, if it's a Gaussian, we have done Gaussian model. Simpler to say, Gaussian model. Normal density function is a model. For, you know the normal for one random variable. What about two random variable? So something like fxy, x. You know the case for one random the variable. So I'll spell out ones. That's about all I'm gonna do. So here is, so 1, 2, similar to the case for one random variable, except a couple of more parameters come into picture. I'm going to look at this rho xy by looking this way, looking from up to down, things like that. Exponential function. Two 1 minus rho xy. Strictly speaking, I should say capital letter y square. If x and y are uncorrelated, that rho xy, rho is called the coefficient of correlation, or correlation coefficient is equal to 0, because no correlation. But in this case, it's a general exponential function. Oh, it's already exponential function. Sigma x squared 1 minus x minus mu x squared plus sigma y squared y minus mu y squared. One more term, and that's about all you will write once in your life, and you will use when you solve the problems. Problem set minus 2 xy x minus mu x y minus mu y squared So a little bit long, a little bit lengthy, but it's not bad. Everything is under the exponential function. Okay? Messy a little bit. If the x and y are uncorrelated, the rho xy is 0. No correlation, which means this is just a half. This third term is equal to 0. That is simply have this two term and that term. This is equal to 0 too. So here I'm going to give a definition first, then we'll derive out the relation. Correlation coefficient or coefficient of correlation is really same thing. Question is equal to you know sigma x, sigma y, all that. So this item is called sigma xy, which is called covariance. I have assigned some homeworks to really derive down the relation using the covariance. This is the covariance, and this is this rho xy. Sigma xy is covariance. Covariance is like for the single random variable, that's like a variance, right? If it's two random variable, in front of the variance, co-CO you have to add into it. This is because this is really for two random variables are involved. So now this is you can say that which is a sigma xy and sigma x, sigma y. Don't confuse, don't feel, God, there are so many definitions. To get down to understand the probability model, you need to understand the parameters. Nothing difficult, it's all the defining process. That's about all we are having it. If x, y are statistically independent, okay, I want you to write out this fxy Right now you can write. So you wrote up to all there. So if it's independent, no correlation, x and y are independent. So this guy has to be equal to 0. Independent means row x, y, no correlation, then that's equal to 0, which means this guy is 0, whole thing is equal to 1, okay? And now this guy is equal to 0, then it's a 2, and then this guy has to go. Very straightforward. Then what happened? So looks like I have to write down, which is 1 over square root of 2 pi sigma x times square root of 2 pi sigma y. Can I rewrite this guys like this? Yes. Then now exponential function of 2 terms x minus mu x squared sigma x squared plus sigma y squared y minus mu y squared. This is exponential e to the something plus something is equal to e to the something times e to the something. Then I can associate this guy with the first one, and the second term associate with this. If you do that, then you can tell right away here this is equal to fx x fy y, right? It's very nice, isn't it? Is it clear? Okay, on Wednesday I'm going to do one more item in joint probability function. I'm going to introduce the conditional probability, very basic item. Like, what is the conditional probability? Then after that, I'm going to talk about the additional probability properties like skewness, kurtosis, and what's good for it, what's the use of it. Question is, what's the use of it? Okay? Then I'm going to introduce the probability model, which has a skewness in the model, and some applications. So you will do as homework. So by end of next week, not this week, you might start to have a small bi-weekly project I want to pursue. That's the process, okay? And what else we have to talk? Oh, I'll send out all the little handouts, and all this stuff is in my note. Then you have a chance to review once again. Everybody check out from Higyu at least this book. This book I really want you to look at up to the page 50. That's the target. Up to the page 50 is a probability model. So one nice thing on this book is there is a very nice example problem, but there's no exercise problem. I don't think you really need exercise. If you fully understand example problem, then I can make out any problem that you can really try out, okay? And then selectively I'm gonna do the chapter 3, which is really beginning of the reliability, structure reliability. Okay, I'll see you Wednesday. All right.